is a pleasure to introduce this afternoon's speaker, the speaker of the last lecture in today's activity. So, Ed Witten is the Charles Simonyi Professor at the Institute of Advanced Study in Princeton. He is a theoretical physicist who has made many important contributions to both physics and mathematics. Ed was an early adopter of superstring theory, an area in which he has worked since. And when string theory was first widely adopted, there were 5 string theories, and this was an embarrassment, one of which seemed to be related to the real world, and the others were held to be merely of mathematical interest. Professor Witten, or Ed, stunned us by proposing that these 5 theories were all aspects of one underlying theory, which he named M theory. This theory was supported by the identification of these 5 different varieties of the theory by the duality. Ed has worked also on quantum field theories and has shown that these theories play an important role both in physics and mathematics. Today's lecture will explain the application of these ideas to the theory of knots. These many contributions have been recognized by many honors and prizes, too many to recall in full. A partial list is the award of the MacArthur Fellowship, the Dirac Medal of the ICTP, the Fields Medal in 1990, the National Medal of Science, the Clay Research Award, the Newton Medal of the UK Institute of Physics, and the Fundamental Physics Prize in 2012. Ed is a member of the National Academy of Sciences and a foreign member of the Royal Society. The citation for Ed's Fields Medal was written by Michael Atiyah. He wrote, "Professor Witten's work exhibits a unique contribution of mathematical power and physical insight, and his contributions have greatly enriched both fields." With this, I invite Ed to give the closing lecture of today's meeting.
So thanks, Phil, for the kind introduction, and thanks to the math department and also to the Clay Math Institute for the invitation to lecture today. It's a real honor to be able to participate in inaugurating the wonderful new building here. So the first 3 lecturers today, roughly speaking, all gave their views of one of the 6 remaining unsolved Clay Millennium problems. And while I might have done that myself, I chose not to because I actually have previously lectured about it and even written up a view of the problem, and a prior version with Arthur Jeffy. So what I'm going to do today instead is to give a lecture that maybe will help show the interests of this problem for mathematicians. And we'll do that in the context of talking about knots, and specifically about the Jones polynomial, which is an invariant of a knot or link in ordinary 3-dimensional space that was discovered about 30 years ago, originally in a completely different context involving polynomials. It had many descriptions and also many generalizations that were discovered soon after Jones's original work. And they all, starting with Jones's work, used 2-dimensional statistical mechanics or mathematics in one way or another. I don't want to assume that everyone is familiar with the Jones polynomial, so I'm going to explain one of the original definitions. For brevity, what I'll explain is called the Vertex Model that was developed in the 80s by Luke Hoffman and others. We start with a knot in 3-dimensional space, but we project it to the plane. If you like, we project it to the plane of the screen. We project it in such a way that there only are simple crossings, and also so that the vertical function, the height function on the screen, has only simple maxima and minima. For example, there's a simple minimum here and a local maximum here. I perhaps should have drawn that a little bit more carefully to make sure that they're really simple. Given such a projection, you divide the diagram in pieces that are separated by the minima, the maxima, and also the crossings. You label each interval between the minima and maxima crossings by a symbol, plus or minus, and then you sum over all such labelings with a suitable factor for each crossing. For each crossing, maximum or minimum. The maximum and minimum are on the next page. What I've drawn here, though, are all the 12 possible crossings, in which the number of pluses at the bottom is the same as the number of pluses at the top. For example, here there's 1 plus at the bottom and 1 plus at the top. So there are 12 such configurations, And to each of them you attach a simple function of a variable q, as written there. And you also, for each creation or annihilation event, where the number of pluses and minuses is now required to be equal, you again give a simple factor as written here. I is just the square root of minus 1. So we have a simple function of q for every crossing, minimum, or maximum. And then, given or not, we just do a discrete version of what physicists would call lattice statistical mechanics, or not. We assign a symbol plus or minus to every segment between maxima, minima, and crossings. We sum over all the possible labelings of these factors. And by the time we're finished, we get a Laurent polynomial in q to the half, which is known as the Jones polynomial. Jones used a slightly different normalization that actually gave a Laurent polynomial in q. Now, the recipe for computing this function obviously depended on the choice of a projection of the knot through the plane. But the output of the finite sum is actually an invariant. This Jones polynomial depends only on the knot, and not on how you chose to project it through the plane. If you're inspired to think that this is true, it's not that hard to check the relations, the right relations that you need to know in order to show that this is in fact a knot invariant. But it's a little bit untransparent why it would miraculously turn out to be an invariant. Now, many of the formulations of the Jones polynomial were discovered in the 1980s. The one that was most illuminating for me, which I believe may have been drawn to my attention by Graham Siegel, was found by Tsuchiya and Kanya, who showed that certain representations of the braid group, which Jones had also discovered, and which were the basis for one of the constructions of the Jones polynomial, also arise from something that string theorists were studying in the period, which is two-dimensional conformal field theory and the associated kinetic exohomologic operations. Their work showed how to generalize the Jones polynomial in a unified way to a much larger class of constructions. They showed that for every simple Lie group G and every representation R, they could construct an analog of the Jones polynomial. So there were, in the same period, other related constructions like quantum groups, which, again, show that the construction ultimately involves a Lie group and a representation. So with these clues and others, I found in 1988 a description of the Jones polynomial in terms of three-dimensional gauge theory. So the new look, in the title of the talk about a new look at the Jones polynomial, has to do with a re-examination of this construction with some hindsight. But first I'll review for you what the construction was. So we know that the invariants we're trying to construct involve a choice of a Lie group. So we pick a compact Lie group G. To simplify the talk in a minor way, I shall assume that G is simple and simply connected. And then we're going to work on some oriented three-manifold M, which could be a compact three-manifold, or it could be something that looks like R3. Or it might even have several M's that each look like R3. And we endow M with a G bundle, which I call E. Then we pick a connection on the G bundle. I call the connection A. I seem to have forgotten to write that. And it's a fact of life that a connection for on a G bundle on a three-manifold has got what's called a Chern-Simons invariant. So if you trivialize for simplicity, we'll assume our bundle is trivial, and so a connection can be represented by one form valued in the Lie algebra. And in that case, the Chern-Simons invariant is given by this simple integral. All we really need to know about it for today is that it's gauge invariant modulo 2 pi times integers. Okay, sometimes people divide by 2 pi and say it's gauge invariant mod integers, but I shall normalize it this way. It's an unusual gauge invariant. All the other gauge invariant expressions you could write, made from a connection on a manifold, would somehow be constructed as integrals of the curvature and its covariant derivatives. The Chern-Simons invariant has the unique property that it's gauge invariant, or more precisely, it's gauge invariant modulo a certain period of 2 pi times an integer, although it's not the integral of the gauge invariant quantity. That enables it to play a unique role in many problems of physics and mathematical physics. Now, following Feynman, we now formally define the Feynman path integral, which is supposed to be an integral over the infinite dimensional affine space of connections. Well, what are we going to integrate? We have this Chern-Simons function that's defined, that's gauge invariant modulo 2 pi times an integer. So we multiply it by ik, where k should be an integer, and exponentiate. So by taking the exponential of ik times Chern-Simons, we get a well-defined map to a circle. Given a gauge field, this is a well-defined complex number of modulus 1. And then, by analogy with what Feynman told us to do in quantum field theory, we integrate that function over the infinite dimensional space of connections, and we divide by the volume of the gauge group. So that's a basic construction in quantum field theory. Understanding it better is actually one of the Clay millennium problems. And it is one of the Clay millennium problems because it's still difficult to understand from a mathematical point of view. So I've already told you that k should be integer because the Chern-Simons function was only gauge invariant modulo 2 pi times an integer. Now, formally, this integral is an invariant of an oriented three-dimensional. I should have perhaps said that we assumed an orientation when we defined the Chern-Simons function. But if you follow the logic of what physicists call renormalization theory, which was introduced in quantum field theory by Feynman and his contemporaries around 1950, then we find that M actually should be what's called a framed three-manifold. That means a three-manifold with a homotopy class of trivializations of its tangent bundle, with a simple behavior under a change of frame. But you can think of that as a technical detail. If you haven't met this at all before, just think of M as an oriented three-manifold. So there was no Riemannian metric in the definition of the Chern-Simons function. The only structure we had on M was an orientation, so that we could integrate a three-form and get a number. So formally, this integral, if it makes sense, is trying to be an invariant of an oriented three-manifold. Now, what do we do if we want to include a knot? Well, a knot is an embedded oriented circle K in M. And if we're doing gauge theory, we can consider the holonomy of the gauge connection A around K. So, mathematicians just call it the holonomy. Physicists in Dyson write it as a path-ordered product. But however you write your holonomies, you take the holonomy of the connection around K, and then you take its trace in the representation R. And this gives a function of connections that depends on the choice of a knot labeled by a representation. And if we had a link consisting of several disjoint embedded knots, we could label each one by its own representation and consider this case or different product of several knots, each labeled by a different representation possible. So of course, holonomy is a 19th century concept, but in the context of quantum field theory, it's called the Wilson Lymphoma theory. It became important in physics in connection with quantum chromodynamics in the 70s when Wilson introduced it in connection with studying what's called quark confinement. He wasn't literally the first person to consider holonomy as a quantum operator, but probably he was the first person to do something important with it. So this is an example, but the world is still full of opportunities to take some 19th century concept, be the first to use it in quantum theory, and get it named after you. So formally now we can define a natural invariant of the pair consisting of a three-dimensional M with an embedded knot. And that invariant is the integral over the space of connections of what we had before times the holonomy. So this gives an invariant of the pair M and K, except that if you apply the lessons you might have learned as a physics graduate student studying renormalization, you'll learn after a little while that both M and K should be framed, which in the case of K is related to what the condensed matter physicists call fractional statistics. Now, if we specialize to the case that M is simply R3, and we take G to be everybody's first example of a compact non-abelian simple group, namely SU2, and take R to be the most obvious representation of SU2, the two-dimensional representation, then this invariant turns out to be the Jones polynomial evaluated at a special value. It's a primitive k plus 2 to the root of unity, but it's not any old k plus 2 to the root of unity. It's, roughly speaking, the one which is closest to 1. So the analog of this for any simple lever is, as I've written, where h is the dual Coxeter number, I seem to have forgotten that, and mg is the ratio of length squared of long and short roots. Now, this is only a discrete set of values of q, but of course these values are enough to determine a Laurent polynomial. So, in a sense, this is a manifestly topologically invariant characterization of the Jones polynomial. Namely, if the magnitude of special values enough to uniquely determine it are given by a formula that physicists regard as a manifest topological invariance, although for mathematicians it's a cousin of one of the Clay-William problems. Now, the argument that the invariant that we get this way coincides with the Jones polynomial at a special value involves making contact with the work of Tsuchiya and Kanya, which I mentioned before, who had interpreted the Jones polynomial in terms of conformal blocks of two-dimensional conformal field theory. So there's a link here between three-dimensional topological field theory, the three-dimensional gauge theory I'm talking about didn't use a metric on M, it just treated M as an oriented tree manifold. There's a link here between topological field theory in 3 dimensions and conformal field theory in 2 dimensions. That link has actually been important in contemporary developments in condensed matter physics, starting with insights about the quantum Hall effect as well as more modern topics, like topological insulators. But we'll have to leave that for another occasion. Now, the 3-dimensional gauge theory gives a definition of the Jones polynomial, or at least it gives a formula for it at an infinite discrete set of roots of unity with manifest 3-dimensional symmetry. We didn't a priori make any choice of a projection to a plane, for example. But there actually were these 2 things that many non-theorists didn't like. So, one I've told you already, the framework for integration over function spaces is more or less the way particle physicists make a living, but it's kind of unfamiliar to mathematicians. So a version of that, as I mentioned, is one of the Clay-William problems. I'll remark, though, that presumably the present problem is a much simpler cousin of the problem that actually is one of the Clay-William problems. For one thing, it deals with a case in which the path interval can be completely evaluated, at least to the satisfaction of physicists. Now, the second thing that I suspect many non-theorists don't like about this explanation is that it does not give a direct explanation of why the Jones polynomial is a polynomial. So most other approaches to the Jones polynomial, including the one I started with involving the Vertex Model, and the approach by Tsuchiya and Kanya, and more or less everything else, do not obviously give a topological invariant, but they do obviously give a Laurent polynomial. So we were here at the opposite situation. But before panicking, we should notice that for most 3 manifolds, the answer we got is actually the correct one. So it's special to knobs in R3 that the quantum invariant, that the invariant you get from the quantum theory, is naturally expressed in terms of Q as a in general, K is the right variable. If you're on a generic 3-manifold M, as far as is understood even today, you can define quantum invariants that depend on an integer K, but they don't have a natural continuation to functions of a complex variable Q without losing some of the 3-dimensional symmetry. There's a slight generalization, which is that in algebraic treatments, you can consider primitive K plus H roots of unity other than the ones that were natural in what I said. The 3-manifold invariants are the same, though. They differ by automorphism of the roots of unity. But maybe there's some non-theoretic content in that generalization. But anyway, roughly speaking, for general 3-manifold, the fact that the theory is only defined with integer values is the right answer. But we're missing something in the case of nonce in R3, because for nonce in R3, it's true that the answers are naturally expressed as long polynomials in Q, rather than simply evaluating them at certain roots of unity. So I think that it's hard to remember what I thought 25 years ago, but probably I just accepted this as a fact of life. The gauge theory gives directly a good picture or a general three-dimensional M, but it's not the most, it doesn't give a very direct explanation of some special things that happen in R3. If you want to understand, starting from the gauge theory, why the Jones polynomial is a polynomial, you really have to first relate the three-dimensional gauge theory to some other approach, such as that of Tsuchiya and Kanye. But around the year 2000, two things happened that gave clues that there should be another explanation. So one development was Polynomial. But what I have to say about it, unfortunately, won't fit into today's lecture. So come back tomorrow at 9. The other development, which began at roughly the same time, was something called the volume conjecture. And I do want to tell you a few words about that and about how it motivated me to take a new look at the Jones polynomial. Because what I'll be explaining really started by trying to understand the volume conjecture. Now, since I won't have time to go into much detail, I'd like to stress that I don't claim to have a physicist's proof of the volume conjecture. In fact, I'm not even completely convinced it's true. Because the result of my work was to suggest it would be true generically, but I at least did not have a reason it was always true. But in understanding just a few preliminaries of the Jones polynomial, in understanding just a few preliminaries concerning the volume invariance, the volume conjecture, I did stumble upon a new viewpoint on the Jones polynomial. That's what I'm really aiming to tell you about today. So, since the volume conjecture will only be important for motivation, I'm only going to give a hint about what it actually says. To orient ourselves, we'll go back for the moment to an oriented three manifold, and we'll ask how this integral behaves for large K. Well, you see, for large K, it's an oscillatory integral. What we're integrating, first of all, is a complex number of modulus 1. And so the modulus is 1, but the phase can oscillate. And when K is large, the phase oscillates very fast. So you might want to practice by understanding an ordinary oscillatory integral, like the integral that defines the area function. So the area function is defined by this formula, where we assume to begin with that K and T are real, although I won't quite go in that direction today, but one can analytically continue beyond real K and T. For real K and T, it's an oscillatory integral similar to the Chern-Simons integral. It's not absolutely convergent, but the oscillations are so rapid at infinity that it's naturally defined as a real number. It needs a slight explanation about how to treat the large X region, but virtually any treatment gives the same answer. And part of some of that is involved in defining the Chern-Simons integral. So when K goes to infinity for fixed T, so depending on whether T is positive or negative, the exponent may or may not have critical points on the path of integration, which is the real axis. So if there are no real critical points, T is positive, then actually that integral vanishes exponentially fast for large K because of the oscillations. But if T is negative, there are real critical points, and the contributions near the real critical points doesn't decay, has no reason to decay exponentially for large K because the oscillations vanish there. So it's a bit of classical mathematics that this kind of integral has the large K behavior I've told you. It vanishes exponentially or it's oscillatory based on whether or not there are real critical points. Now, Feynman taught us to apply the same kind of logic to infinite dimensional Feynman integrals. And so we do that here for this infinite dimensional integral. So we have to ask, what are the real critical points? Well, the critical points of the Chern-Simons function are flat dimensions. Because if you go back to the derivative of the Chern-Simons, if you go back to the definition of the Chern-Simons function, you'll find that its variation at a connection A is proportional to the curvature of that connection. So a critical point is a flat connection that corresponds to a homomorphism from the fundamental group of M to G. And therefore, the asymptotic behavior of the quantum invariant for large K is given by some of oscillatory contributions associated to such homomorphisms. So there are precise formulas for Z, K of M from all kinds of methods, quantum groups, grade representations, different methods. But regardless of the approach, there are formulas for Z, K of M. If you study these formulas for large K, you do find that the asymptotic behavior is what you would expect from the formal Chern-Simons path integral. So originally this was verified in special cases by Friedlander and by Lisa Jeffrey. So what I've told you so far is on general three manifolds where K has to be an integer. But now let's specialize to knobs in R3 where K does not have to be an integer. Because in fact, the answer is most naturally expressed in terms of the complex variable Q as a polynomial. So in discussing the volume conjecture, it's usually assumed that G is SU2, and the representation is the n-dimensional irreducible representation of SU2. The not invariant that goes with that representation is usually called the colored-Jones polynomial. Then we take K to infinity through non-integer values with fixed K over M. That's what we couldn't do on a general three manifold, because on a general three manifold, we don't have a natural continuation away from integer K. Well, in R3 we do. So, in fact, the people doing this work don't express what they're doing in terms of K. But to express it in my language, we take K and M to infinity with a fixed ratio, but with K going to infinity through non-integer values. So it's not the most general thing we could do, but a typical thing we could do is to fix a complex number K0, and then let K be K0 plus M, and then we take N to infinity, and K goes to infinity satisfying this relation. So we could try to analytically continue in the dimension N of the representation, but we don't. We keep that as an integer. So we take K to be K0 plus M. N goes to infinity, so K over N goes to 1, but it goes to 1 in this particular case. And now it turns out that the large N behavior is still a sum of contributions of critical points, but now, as you might suspect, in general, they are complex critical points. By a complex critical point, I mean simply a critical point of the analytic continuation of the Chern-Simons function. We make this analytic continuation in a straightforward way. We replace the gauge group G with its complexification, which I'll call G sub C. And likewise, we replace the G bundle E by its complexification, E sub C. And we replace the connection A by a complex valued connection, curly A, on E sub C. We can think of it as a complex valued connection. And then the Chern-Simons function can be analytically continued to a holomorphic function, holomorphic engagement function, on the space of complex valued connections. This function is defined by the same formula we had before, but with ordinary A replaced by curly A. And its gauge invariant to the same extent it was before. Its gauge invariant modulo 2 pi times an integer. So a critical point of the analytically continuous function is simply now a complex valued flat connection corresponding to homomorphism of the fundamental group of M to the complex group G sub C. Now, for the volume conjecture, we take the three manifold to be simply R3. So the fundamental group is trivial. But we're supposed to also include a holonomial or Wilson loop operator involving a trace in the n-dimensional representation. And we're taking that to be a very big representation because we take n to infinity together with k. So it turns out that the right notion of what you mean by a critical point is affected by the polynomial operator. So there's a very nice story today, but I don't want to take. There's a very nice story here, but I don't want to take the time to explain it today. It involves the Borel-Bach theorem and its interpretation in terms of Feynman intervals on the flag interval. That would take us too far afield because we only want very limited information to motivate or point us in the right direction. So I'll just say that the right answer turns out to be that what you should mean by a critical point in the connection presence of a knot is a flat connection of the knot complement with a given conjugacy class of the holonomial around the knot. So what's shown in the work on the volume conjecture is that typically, if we take n to infinity, with k being a fixed complex number k0 plus n, then the asymptotic behavior of the Collar-Jones polynomial is governed by such a complex critical point. Now, physicists know various situations involving tunneling problems. That's one example, and transmission through a barrier is a second. Also, scattering above the barrier. There are various situations in real physics, originally nuclear physics involving alpha decay, but many examples, in which a path integral is dominated by a complex critical point. But it's always, in real physics, a complex critical point that makes an exponentially small contribution. What really surprised me about the volume conjecture is that for many knots, the dominant critical point makes an exponentially large contribution. In other words, if we take n to infinity, this is meant to be k as k0 plus n, not equal to n. So if we take n to infinity with k being offset from n, if k naught is an integer, then the Collar-Jones polynomial has oscillatory behavior. But as soon as the offset is not an integer, actually even if it's real, then the Collar-Jones polynomial has exponential growth for large n. And concretely that happens because k times Chern-Simons has a negative imaginary part. So the integrand, which is the exponential of ik times Chern-Simons, grows exponentially for large k. So I knew very well that ordinarily in physics, when you see a complex critical point, its contribution is exponentially small. And it really bothered me that in this problem there were exponentially big contributions. So it puzzled me for quite a while, but it turns out that you can find an ordinary integral that does the same thing. So I've written down a one-dimensional integral that captures the essential phenomenon that's going on in the Collar-Jones polynomial. It's actually an integral representation of a Bessel function. If you regard this as for fixed k as a function of n, then it solves Bessel's equation. And we want to think of Bessel's equation as a baby version of all the conditions of quantum field theory that you have to understand to win your $1 million play prize for the mining problem. So when we generalize this, we're going to insist on maintaining Bessel's equation. We think of k as an analog of the integer valued parameter in the theory, which we also call k, and in the analogy, n corresponds to the dimension of the representation. The analogy is perfect because in this problem, n doesn't have to be an integer, while in the Chern-Simons case it did. But it turns out that the analogy is good enough to illustrate things that were puzzling me. Now, if we take k and n to infinity with a fixed real ratio, so k is naturally an integer, and you keep k over n real, then the integral has oscillatory behavior. How do you understand it? Well, the exponent, what we're intimating is the exponential of I times the function I've written here, and the integral will vanish exponentially for large k and n unless f has critical points. So if k over n, if the ratio of k over n is such that there are critical points on the circle, we'll get oscillatory behavior for large k and n, and if there are no real critical points on the circle, we'll get exponential decay for large k. But what can we do to get exponential growth for large k? Well, to imitate the situation considered in the volume conjecture, we want to analytically continue away from integer values of k. So to do that, first we set z equal e to the I theta, so that we're doing an integral in the complex plane on the unit circle. But in that form, k should still be an integer. To get away from integer values while still obeying Bessel's equation, we have to change the integration contour. This is meant to be 0 in the complex z-plane, this is the unit circle. And now we take a contour that has a long tail going off to z equals minus infinity. If k is an integer, we haven't changed anything, because the tail that we've added, the two pieces of the tail cancel. However, now we can analytically continue away from integer k, I think as long as the real part of n is positive. If the real part of n is positive, then the integral I've written actually converges for any k, and not only that, but it obeys Bessel's equation. When you try to check whether it obeys Bessel's equation, you have to integrate by parts. And although we've introduced it, the contour is not compact, so you have to worry about surface terms. But this, when the real part of n has the right sign, the surface terms vanish. So we've generalized our baby example of quantum field theory to non-integer k, and we are still satisfying Bessel's equation. So now that we've analytically continued, what's the behavior when k and n go to infinity with a fixed ratio? Well, if k is an integer and n is real, then as I said before, the large k behavior is oscillatory or exponentially damped, depending on the ratio of k over n. But as soon as k is not an integer, even if k and n remain real, the large k behavior can grow exponentially, rather as for the color-Jones polynomial. So this is a baby example that does what actually puzzled me about the color-Jones polynomial, and we can get to the bottom of what's happening. So it's elementary to prove what I just said about the large k behavior about integral in a certain range, but again it would take us a little too far afield, so I'm not going to actually explain that as sympathetic behavior. What I instead will only tell you the technique one can use to analyze it. So the technique one needs to use to analyze the behavior of this integral is the technique we will follow when taking a new look at the Jones polynomial. So, in general, we're trying to do an integral of the form the integral of k times f of z over the complex plane, where f is some homomorphic function, and gamma is a cycle, which might be compact, or if it's not compact, it's at least a cycle in which the integral converges. So, in our case, f is this function I've written here. But you see the function f is actually multi-valued because of the logarithm. So I'd rather go someplace where f is multi-valued. For this, we work not with z, but with the variable w, which is log z. And then in terms of w, f is single valued. And so now, in general, we're doing this kind of integral, the integral dw of the exponential k, times a single valued homomorphic function, and we're integrating over some cycle in which the integral converges, and we want to know how k is for large k. So, the general way to answer that question is to use Morse theory, and first understand all possible cycles in which the integral would have converged. So, to do this, you take the real part of the exponent and regard it as a Morse function. So the real part of the exponent is a smooth function, h. It's neither holomorphic nor anti-holomorphic, so I write it as h of w and w bar. The critical points of h are simply the critical points of the holomorphic function f. So remember, critical point is a point where the derivative vanishes. So for our particular f, the derivative of f is this big, and it vanishes when that equation is spade. Those are also the critical points of h. The key step is now the following. To every critical point p of h, we define an integration cycle that I'll call gamma p, which is called a Lefschetz symbol, on which the integral we're trying to do converges. So the Lefschetz symbol is defined using what's called the gradient flow equation of Morse theory. We take a complete metric on the w plane. We might as well take the obvious scalar metric. And then we write down the gradient flow equation. It means that we introduce a time variable called t. You starting someplace on the w plane, you flow downward in the direction given in which h decreases as fast as possible. So the gradient flow equation for the obvious flat metric is this one. And the left-hand symbol is the space of all values of t equals 0 of solutions of the gradient flow equation on the semi-infinite interval from minus infinity to 0 that start at p at time minus infinity. So I've drawn a picture here. So all critical points in this case are going to be saddle points because the real part of a holomorphic function is harmonic. It doesn't have a local maximum or minimum. Its critical points are saddle points. So I've drawn a saddle point. It goes up this way and it goes down this way. And the left-shift symbol is the way it goes down. So in our one-dimensional example, the left-shift symbol associated to p is simply the contour of steepest descent of the real part of the exponent in the W. Now, the cycle, gamma p, is not compact, but the Morse function goes to minus infinity at its ends. So, experts will know that I'm ignoring Stokes' phenomena, but the statement is true for generic value of complex parameter k. So, even though the cycle isn't compact, the integral we're interested in converges along that cycle. And not only it converges, but it's straightforward to answer the question of how that integral behaves for large k. When k goes to infinity, the cycle is defined so that the exponent, the real part of the exponent, has a unique maximum along the cycle. And for large k, that's going to dominate the integral. So for large k, the integral can be dominated by the value at the saddle points with a series that you calculate by expanding around the critical point. Now, what you learn from Morse theory is that any cycle in which the integral converges can be expanded in terms of the left-shift symbols with integer coefficients. And after computing the integers a sub p, it's straightforward to determine the large k asymptotics of the integral over a cycle gamma. The asymptotics is known for every gamma p. So you simply take the AP, you simply take the value of p where gamma p is maximal, subject to AP being non-zero. And that will give you the asymptotics of gamma, the integral of gamma. So if you apply this procedure to our integral, we can learn what I said before. The integral has the same qualitative behavior as the Color-Jones polynomial. The limit where n goes to infinity and k is n plus a constant has a very different behavior depending on whether k naught is an integer. If k naught is not an integer, the large k asymptotics is dominated by two left-shift symbols whose contributions cancel whenever k is an integer. Concretely, so, anyway, this is how a Tory integral can exhibit the behavior that's actually found from Color-Jones polynomial. Now, at this stage, I hope it's clear, not only to physicists present, what we should do to understand the analytic continuation to non-integer k of the quantum invariant of knots in R3. And also to understand the asymptotic behavior of the Color-Jones polynomial that's studied in the volume projection. We should define left-shift symbols in the space curly U of complex projections. And in the H3 definition of the Jones polynomial, we should replace the traditional integral over the space U of real connections with a sum of integrals over left-shift symbols. However, it's probably not clear that this will actually lead to a useful new understanding of the Jones polynomial. It wasn't clear to me when I got this far. So, what is the left-shift symbol going to be? To define the left-shift symbols that we want, we have to consider a gradient flow equation on the whole infinite-dimensional space curly U of complex value connections. And in this gradient flow equation, we take the Morse function to be the real part of the exponent of the Feynman path interval. Since this will perhaps be unfamiliar to those who don't work on Donaldson and floor theory, I'm going to practice with a slightly simpler case. Well, I'll start with the simpler case that actually is studied in Donaldson and floor theory, because I can explain it more quickly and it will be familiar at least to some of you. So, instead of gradient flow on the space of complex connections, suppose we were trying to do gradient flow on the space of real connections, with the Morse function being the Chern-Simons function. Well, first, to define gradient flow, we need a Riemannian metric. So we pick a Riemannian metric of the three-manifold M, and that gives a Riemannian metric of the space of connections by this formula for the norm of a small displacement or a small variation delta A of a connection. So since we have a metric on the space of connections, and we also have a Morse function on the space of connections, namely the Chern-Simons function, we can define a gradient flow equation. The gradient flow equation will be a differential equation on the four-manifold. So to define the gradient flow equation, we always introduce a new time variable. But now we already have a three-manifold. So what we're flowing is a connection on three dimensions, and the flow will give a one-parameter family of a three-dimensional equation, which you can think of as, in terms of fields on a four-manifold, which will be m times r, where r is the flow direction. Concretely, the flow equation is that the time derivative of the connection is minus the gradient of Chern-Simons. But I actually used before the fact that the critical points of Chern-Simons are flat connections. So that's the statement that the gradient of Chern-Simons is the curvature, so that the critical points of Chern-Simons have to do with representations of the fundamentalism. So we could write this equation for an arbitrary Morse function, but generally it would be a very bad equation. Well, what does bad be? Well, what does good mean? There are good classes of differential equations, like parabolic ones or elliptic ones, and then the generic thing you could write down is bad. You won't have any kind of nice theory. But this happens to be a good case. So if we did this for a random Morse function or in some random situation, we would not get an elliptic differential equation, and we would not get an equation with four-dimensional symmetry. As defined, the problem was on a one-parameter family of three-manifolds. So there's no reason obvious to get anything with four-dimensional symmetry, but something that's actually well known to people who work on Donaldson and floor theory is that some miracles happen here. The flow equation for the Chern-Simons equation actually is an elliptic differential equation that has full four-dimensional symmetry. It's not just any old elliptic differential equation. It's the instanton equation that's important both in four-manifold theory and also in quantum field theory. It has four-dimensional symmetry, meaning it's naturally defined on any oriented four-manifold X, not necessarily of the kind that appears in our derivation. So these miracles are well known to researchers exploring Donaldson theory, where they play an important role. So the same thing happens when we do gradient flow in our situation, not with the ordinary Chern-Simons function, but with the real part of the holomorphic Chern-Simons function as a Morse function. And also, we pick the obvious antimetrical space of complex connections. So the same things happen, but I won't go through the derivation because I think we get too tangled up in too many details. But what happens is the same thing that happens to the benefit of people who work on floor theory. The gradient flow equation is a gauge-fixed version of an elliptic differential equation with the full four-dimensional symmetry. This equation is a four-dimensional cousin of Hitchin's celebrated equation in two dimensions. It's an equation for a pair, A and phi, where A is a connection on a G bundle E. That means A is a real connection, a unitary connection, with structure of the compact Lie group. And phi, as in Hitchin's work, is a one form with values in the echelon bundle. And the equations look like this. I've written the equations in a way that exhibits the fact that they're defined in any oriented form with a Riemannian metric. The only structure used is the Hodge structure. So X here can be any oriented Riemannian four manifold, but in the particular case, with X as a product of a three manifold times a one manifold, this is the gradient flow equation that we have to use to define Lefschetz symbols. So I've written them in four-dimensional terms, but they're flow equations for the three-dimensional complex connection A plus I prime. Now, something else unexpected happens, though it took at least a year before I took it seriously. The equations one gets here are actually equations that I had studied before in my work with combustion on gauge theory and geometric landlines. So that turns out to be important, but not answering any questions I've mentioned so far. So for now, we'll just leave it on the side and then we'll go back to it. So also these equations have been studied more recently in some mathematical works by Talos and also by Gallardo and Wilson. So remember, the reason we wanted these equations is that we wanted to define Lefschetz symbols in the space of complex connections in the three manifold. So now we can say what a Lefschetz symbol would be. Well, there's supposed to be a Lefschetz symbol for every complex critical point. A complex critical point is a phi connection on the three manifold. So we take a representation of the fundamental group into the complex Lie group. That gives us a complex phi connection, which is a critical point. And for that critical point, we're supposed to define a Lefschetz symbol. So we work on a four manifold, which is n times a half line, because ordinary Lefschetz symbols involve solving the gradient flow equation on a half line. So here's the picture. Here's n, which is a three manifold, and here's a half line. And n might have a knot in it, although actually what I drawn is more linked than a knot. And we define a symbol of gamma rho for every representation of the fundamental group to consist of all flat connections on the boundary that are boundary values of solutions of the KW equations, the gradient flow equations for complex transitions, on m times r plus, that approach the given critical point at infinity. So that's what a Lefschetz symbol means in this situation. Actually, for the case where the connection is real, floor theory can be thought of as homology of such middle-dimensional cycles, analogous to this Lefschetz symbol. But in conventional floor theory, those cycles are not used as integration cycles. The new twist here is that if you like, the middle-dimensional cycle of floor is interpreted as a Lefschetz symbol and will be an integration cycle. So for a general choice of n, there would be various choices of representations of the fundamental group. And then to understand the quantum knot invariance in this way, we need to express the integration cycle of the traditional quantum knot invariance, the integration cycle of real connections, in terms of Lefschetz symbols. That's technically tricky, and actually leads to a complicated answer because there will be Stokes phenomena. So now I can tell you why knots on R3 are special. Knots on R3 are special because R3 is simply connected. So some of the statements would work on S3, but some will not, so I will use R3. Since R3 is simply connected, it only has one representation of the fundamental group, the trivial one. So there's only one Lefschetz symbol. And therefore, I can tell you the relation between the integration cycle of usual quantum knot invariance and the Lefschetz symbol. They're the same. Because when there's only one critical point, more straight tells us that there's essentially only one possible integration cycle. So instead of defining the Jones polynomial by integration over the space of unitary connections, real connections of the compact region, we can define the Jones polynomial by integration over a Lefschetz symbol. So I can write the Jones polynomial this way. Now instead of integrating over real connections, we integrate over those complex connections that are boundary values of solutions of the KW equations on a four manifold. So now what good is this? That's one question. Another question is how much time? If we have 10 minutes, we're just about one track. My work with Wilson had involved what physicists call a twisted version of maximally supersymmetric Yang-Mills theory in 4 dimensions. We showed that this twisted version was related to the geometric Langlands correspondence. But there's an aspect of that twisted theory that we didn't use very deeply in our work on geometric Langlands, but which we certainly discussed, which is that the twisted theory localizes on the space of solutions of these KW equations. The same KW equations that are used in defining the Lefschetz symbol. So, in this case of this particular formalical, the space of solutions of the KW equations, if we ask for the fields to go to 0, that is a critical point down here, and we impose no condition here, then the space on which the path integral of the supersymmetric gauge theory is localized is just the Lefschetz symbol, over which we have to integrate to get the Jones polynomial. So the upshot of that is that instead of defining the Jones polynomial as a path integral for a Chern-Simons gauge theory in 3 dimensions, we can compute it for a path integral of a supersymmetric gauge theory in 4 dimensions on a half space, which is R3 times the half line, with a slightly unusual boundary condition on the boundary of the half space. Now, actually, this is a description of Jones polynomial that's even a little bit closer to the plane line problem, because now we're doing gauge theory in 4 dimensions. And the action is more similar to the action assumed in the Clay problem. But unfortunately, until quantum field theory is more familiar, it's going to be a hard answer for mathematicians to understand, just like the formula we started with at the beginning, in terms of integration over the space of real connections. Because, as I said before, quantum physicists make their living with infinite dimensional integration, but most mathematicians don't. But there's one more step that brings us into a world that actually is accessible mathematically, and gives a new, so it will give us in a moment a new definition, a new characterization, what I claim is a new characterization of the Jones polynomial, that definitely could be studied mathematically, as well as a new explanation of why the Jones polynomial is a lower polynomial in Q. The step in question was also important in my work with Witten, and it's one of the main tools that physicists use in studying the supersymmetric gauge theory in question. This is the 4-dimensional analog of mirror symmetry. The 4-dimensional analog of mirror symmetry is called electromagnetic duality. It's the basic duality that Wilson and I related to geometric Langlands, and it has got all kinds of other manifestations in physics and mathematical physics. So we want to apply electromagnetic duality to our present problem. In order to do this, we have to, so the electromagnetic duality projection will be very familiar to physicists, but the boundary condition we're using here is a little unusual, and we need to know what it transforms into under electromagnetic duality. That's actually the analog in 4 dimensions of a problem mathematicians study a lot in 2 dimensions, except they don't formulate it in 2 dimensions as physicists would. In mirror symmetry, you have to ask what's the object in the Fukaya category that's mirror to a given coherent sheaf. And not everyone here will recognize it, but the question in the last sentence is a 4-dimensional analog of that kind of question. For the particular case of sheaf, the dual boundary condition was described by Garoto and me a number of years ago, so luckily that information is available. It's a slightly unusual elliptic boundary condition, which I'll describe in tomorrow morning's lecture. So today all I'll say is that it has the same property as a standard elliptic boundary condition, which is that it reduces us to finite dimensional spaces of solutions of the KW equation. So now we go back to this situation, and you don't have to study it anymore with infinite dimensional finite integrals. We make a duality transformation to a framework in which the boundary condition cuts the spaces of solutions of the KW equations down to finite dimensional spaces, and all we have to do is imitate Donaldson theory. So the most basic variant in Donaldson theory is to count the number of solutions of the equation under study, where counting means counting with signs. For physicists, the sign has to do with the sign of a Fermi determinant. So here, we count the number, which I call B sub n, of solutions for a given value n of the second Cherenkov. So we're doing gauge theory on the 4 manifold. So modulus in details. A gauge theory of a compact Lie group has a 4-dimensional characteristic class whose integral is the incident number. And we count the number of solutions B sub n for a given incident number. So when we do this counting, the boundary conditions depend on the choice of the knot and the choice of the representation R of the label. So I won't explain all that story today. Just imagine that we have elliptic boundary conditions in the block, and everything goes to 0 at this end, and at this end, there's some mysterious boundary conditions that depend on the knot. Their important property is that they're elliptic boundary conditions. So our elliptic equation will have in the right situation, only finite many solutions. So we count the number of solutions for every incident number. The third integral is a Lonel polynomial in Q, whose coefficients are the number of solutions of the KW equation with incident number n. So that exhibits the Jones polynomial and the related quantum variance of knots in 3 dimensions as Lonel polynomials in Q with integer coefficients. I put Laurent polynomials in quotes because of the subtlety. Powers of Q are shifted from integers in a way that depends upon exactly how the bundle is trivialized near the boundary. So for instance, the Jones polynomial of a knot with this normalization is really Q to the 1/2 times L1 6. So we started with finite integrals and we had a lot of fun with finite integrals. But we reached a description I proposed for the Jones polynomial that we can study without regard to finite integrals. We just have to imitate Donaldson and count the solutions of a somewhat different elliptic partial differential equation in 4 dimensions. Thank you.